Lesson 5.5, Laws of Exponents. Now, our laws of exponents, we're currently going to be dealing with operations on monomials. That's it. Okay, so we want to remember that a monomial is a single term. It can be variables, numbers, exponents, and these are combined with multiplication. There's no addition or subtraction. And we have no variables in the denominator. As exponents or under square roots. Also, no exponents are negative or fractions or decimals. Okay, so that's what a monomial is. When we add monomials, okay, this is the operation or the process of collecting like terms. Okay, like terms have identical variable portions. So the letter and the exponent both have to match. So if we add monomials together, we look for the like terms and we add the coefficients. So let's just do an example. Oops, don't want any subtraction in there. Okay, so when we look at this, I have x's in every term, but only 2 terms have x squared, and only 2 terms have y to the third. These are my like terms, because the variable portions match perfectly, and therefore these are the 2 terms that can be added. I add the 2 and the 3 together, and I get 5x squared y to the third. You'll notice that the exponents did not change. Now the 4xy to the fifth and the 2x didn't match anything, so I couldn't add them together. These were not like terms. So I couldn't do anything with those. Now when we subtract monomials, we are going to do the same process. We're just going to subtract the coefficients. So for example, if I have 4x squared minus 2x to the third minus 3x squared. My 4x squared and my 3x squared are alike, so those are the 2 that I'm going to subtract. And I just put them together because they match. And 4 minus 3 is 1, so that leaves me with 1x squared and this x to the third. Now, if I have a negative in front of the parentheses, so if I'm subtracting in front of the parentheses, let's say it was like this. I need to distribute that negative into and change the signs of both terms inside the parentheses, which would give me 4x squared minus 2x to the third minus 3x squared, which would give me 4x minus 3x squared, which is just 1x squared, and that 2x to the third that didn't match. Okay, so we can only subtract or add when our variables are perfectly matching. They have to be identical. Now, multiplying and dividing monomials, that's a little differently. Okay, when we multiply monomials, we have to follow exponent rules. Okay, now multiplying exponents, we have to, we have to have a common base. And you might recall that if I have an exponent, this is my base, and this is my exponent. So when I multiply monomials, I deal with the common base. When I multiply exponents with a common base, so for example, a to the m times a to the n, I add the exponents. So given an actual x to the third times x to the fifth, that's going to give me x to the 3 plus 5, which is going to give me x to the 8th. The reason this works is because x to the third is 3 x's, x to the fifth is 5 x's, and if you count those up, you have 8 x's altogether. Now, when you multiply a monomial, we're using this rule. What we do is we multiply the like parts. So let's say, for example, I have this monomial, 3x to the third, y to the fourth, z squared, and I want to multiply that by negative 2x, y to the third, z to the fourth. The like parts, 3 and negative 2, are alike. Those are both coefficients. X to the third and x are alike because they're both x's. Y to the fourth and y to the third are alike because they're both y's. And z squared and z to the fourth are alike because they're both z's. So these are the things I'm going to be multiplying. I'm going to multiply 3 and negative 2, x to the third times x, y to the fourth times y to the third, and z squared times z to the fourth. Now you don't have to write it out this way. I just wanted you to see what I'm actually multiplying. Well, 3 times negative 2 is negative 6. If there's no exponent on your variable, it's like an invisible 1 because there's only one x. Multiplying x to the third times x gives me x to the fourth because it's 3 plus 1. Y to the fourth times y to the third gives me y to the seventh because it's 4 plus 3. Z squared times z to the fourth gives me z to the sixth because it's 2 plus 4. So when I multiply those two monomials, this is what answer I will get. Let's do another one. Oops. Let's try okay, now be careful. See how these parentheses are touching? That means multiplication. This is not minus 3y squared a to the third. It's times negative 3y squared a to the third. So I'm going to do 4 times negative 3. So negative 4 times negative 3 gives me positive 12. X times, there's no matching for the x, so I just bring that down. Y to the third times y squared, I have 3 plus 2, that gives me y to the fifth. Z has nothing matching with it, so I just bring that down, z squared. And then I have a and a to the third, so I have 1 plus 3, which gives me a to the fourth. So my answer is 12xy to the fifth, z squared, a to the fourth. Now when we divide monomials, we use the rule for the quotient of powers. And we'll write down all the rules at the end. So dividing monomials uses the rule for dividing exponents. So if I have a common base and I divide, I'm going to subtract. Now the way you can remember this is that multiplication and division are opposite, and so are adding and subtracting. So when we multiply, we add. When we divide, we subtract. So for example, if I have x to the 10th over x to the third, this is the same as x to the 10 minus 3, which gives me x to the 7th. Now if my larger exponent is on the bottom in the denominator, so if I had x to the third over x to the 10th, this is actually the same thing as x to the 3 minus 10, which gives me x to the negative 7th, and we don't allow negative exponents, so we put it in the basement. But you can think of it as a tug of war. I'm still going to subtract 3 from 10, but because 10 is in the denominator, it's going to win the tug of war, so that's where the 7 will exist. Now I can't have a blank numerator, so I enter a 1. Let's try some monomials. Okay, so we're going to do the same general idea. We're going to be dividing like terms. So 6 divides by 3, x's, y's, and z's go together. 6 divided by 3 is 2. 2 over 6 for my exponents. 6 minus 2 is 4, but 6 is bigger, so it's going to win the tug of war, so it'll go in the denominator. 5 minus 5 is 0. So whenever you have the same exponent on the top and the bottom, those are going to cancel each other out completely. If there's nothing else there, it equals 1. But in this case, we'll just leave it blank. And then 10 minus 2 is 8. If we try another one, let's do okay, I have 8 over 12, so 8x to the 9th, y to the 5th, z to the 9th, over 12x to the 3rd, z to the 14th. 8 and 12. 12 does not divide by 8, and 8 does not divide evenly by 12, but these both divide by 4. So I'm going to divide both of them by 4. 8 divided by 4 is 2. 12 divided by 4 is 3. 9 minus 3 is 6, and the 9 is in the numerator, so is the 6. Y has nothing like it, so I just keep it where it is. And then I have z to the 9th and z to the 14th. 14 minus 9 is 5, and 14 is in the denominator, so is the 5. That's how we divide monomials. Okay, we now have something also called the power rule of exponents. So this is when we raise a monomial to a power. Okay, we follow the power rule of exponents. And that tells me if I have some number to an exponent and I raise it to another exponent, I multiply. So for example, if I have x squared and I raise that to the power of 5, that will be x to the 2 times 5, which will give me x to the 10th. And the reason this works is because x squared to the 5th is x squared times x squared times x squared times x squared times x squared. And if I add these all together, I get 2, 4, 6, 8, 10. So this is a shortcut. You just multiply. If you have monomials and you raise them to the power, you distribute the power in. So every single part of the term gets raised to the power. Sorry, I had a small technical glitch, so I don't know exactly where I was, and I'm just going to start over. If I'm raising this monomial to a power of 4, I need to distribute the exponent to each term inside the monomial. So essentially what I'm going to have is 3 to the 4th times x to the 3rd to the 4th times y squared to the 4th. Everything needs to be raised to the power of 4. 3 to the 4th is 3 times 3 times 3 times 3. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81, and then 4 times 3 for my exponent powers is 12, and 2 times 4 is 8. So I get 81, x to the 12th, y to the 8th. Let's try another one. If we take 5, a squared, b to the 9th, c to the 5th, and I raise these to the power of 3. I'm going to distribute this 3 in to every single term inside. It does not matter how many terms there are. You distribute the exponent to everything. 5 to the 3rd is 125. 2 times 3 is 6. 9 times 3 is 27. And 5 times 3 is 15. So that's how we raise a monomial to a power. Okay. Sometimes we have to raise a fractional term to a power. And when that happens, we're going to have a rule called quotient to a power. And it's very similar to raising a product to a power, which is what we just did. If I have some fraction 2/3 and I square it, that's 2/3 times 2/3, which gives me 4/9. That's the same thing as 2 squared over 3 squared, 4/9. So what we're going to do is distribute into the quotient to the numerator and the denominator. So if we have some monomial that's being divided, such as 3x to the 5th, y to the 3rd divided by 4a squared b, and I raise that to the power of 2. I'm going to square the 3 and the x to the 5th and the y to the 3rd, and I'm going to square the 4 and the a squared and the b. So this will be equivalent to 3 squared times x to the 5th squared times y to the 3rd squared over 4 squared times a squared squared times b squared. 3 squared is 9. 5 times 2 is 10. 3 times 2 is 6. 4 squared is 16. 2 times 2 is 4. And then b squared. So let's try a couple of those. Let's not do 4 again. Let's do 2. Okay, and I'm going to raise this to the power of 5. So I'll have 3 to the 5th, which is 81 times 5, which is 243. And then I have 3 times 5, which is 15. 15, not 18. And then 9 times 5, which is 45. And then I have 2 to the 5th, which is 32. And then 5 times 5 is, that's z on x, is 25. Now sometimes we have some common variables inside the parentheses. So for example, let's say I have some expression 10 over 25, and I have x to the 5th, x to the 10th, y to the 3rd, y, and then I raise that to the power of 2. You have a choice. You can simplify first and then raise to the power, or you can go the other way. You can raise to the power and then simplify. When it's a single monomial like this, I think this is the best method. You simplify first, then you're dealing with smaller numbers. 10 and 25 both divide by 5, giving me a 2 and a 5. 10 minus 5 is 5, and 3 minus 1 is 2. Then I square it, and I'll get 4y squared to the 4th. 2 times 2 is 4. And then 5 squared is 25. 5 times 2 is 10. Otherwise, I would have had 100 over 625, and I would have had to reduce that larger number. The exponents would just be subtraction, so that's actually not so bad either way. But when you have those coefficients in there, it can cause some large numbers to have to be reduced. Okay, so let's break down the rules. Okay, you have multiplying exponents with common bases. And that's, when I have like a to the m times a to the n, I add the exponents. Then I have dividing. And that's when I subtract. So that's a to the m minus n. So we have multiplying, we have dividing, we have raising an exponent to a power. So if I have a to the m and I raise it to the power of n, I multiply. have raising a product to a power. So for example, if I have x, let's do a's again, a to the m, b to the n, and I raise that to the p, that's a to the mp, b to the np. And then if the last one I have was raising a quotient to a power. So for example, if I have a to the m over b to the n and I raise it to a p, I'll have a to the mp over b to the mp. So this is kind of a distribution. You're distributing the exponent. And those are the laws of exponents.